Well, I'm absolutely delighted to be joined here today at the Star Spot by Jakub Scholtz. Thanks for coming on to the show.
Oh, thank you very much. It's a pleasure.
Well, this is really fascinating topic here, and it's relatively close to home compared to some of the topics in deep space that we often talk about. This is the idea that you and your collaborators have put out there quite recently, in the last several months, in fact, of the possibility that the so-called Planet 9, which we'll get into, might not be a planet at all, but might actually be a primordial black hole. So that's super fascinating that we'd have a black hole, albeit a really tiny one, so close to our planet. But before we get into that, the concept of Planet 9, just kind of remind us what that is, where that came from.
Right. So I should make it clear that Planet 9 is not our original idea. This is actually an idea that's been tossed around for quite a while. And there's been a dedicated group of people who have been chasing the idea down for, I think, nearly 20 years. Some of those people are Brown, Battigan, Adams, and they've been observing objects that are in the very outer solar system, much past the orbits of Neptune, or even way further than Pluto itself, that have been eventually demoted. And they noticed that some of these objects, their orbits don't appear as random as we expect. And one of the nice explanations for this lack of complete randomness is that there is an object out there that seems to kind of shepherd them around and kind of keeps gently nudging them in such a way that all their orbits seem to kind of point in generally roughly the same directions, that they're more elliptical than you would typically expect, that they are not sitting in the same plane as all orbits of all the known planets. And sort of all these anomalies tend to lead you to believe that maybe there's something extra. And so they call this extra thing a Planet 9. It's quite massive. That all the anomalies indicate that it's really the mass of a planet, not just one extra or asteroid out there. And so that's why they call it Planet 9.
And the models support that it is one unique giant body as opposed to several smaller bodies that might jointly account for this coordinated orbital pattern that we see among these Kuiper Belt objects.
Yes, although interestingly enough, if you replaced that one giant body with a ring of material that has roughly the same mass as that one body, and the ring is kind of the same orbit as that body, you would get actually very similar results.
Okay.
But that would take also some arranging for this ring to kind of be that way. Maybe it was a planet that got shredded or something like this. But yes, in general, you would think of it as really one object. That's a simpler explanation in some sense.
And we'll ask what happens if we replace that one object with a black hole in just a moment. But if it is a planet, how would it have gotten out so far beyond where the traditional 9, or I guess now it's 8 planets of our solar system congregate? Would it have somehow been flung out there from an original orbit closer to the sun, or would it have been captured and its origin would have been outside of our solar system?
So actually, the question you ask is the question exactly that lots of people had come up with, exactly the things you suggest. One of them is you started off in the inner solar system, and then maybe another star passed by and knocked it out, and knocked it up into a higher orbit. That comes with a series of actually issues. One of them is even if you knock something up to orbit quite far away, it tends to come back to where the orbit is such very elongated, and it tends to come back really close to where it used to be. And so you would have to knock it up not just once, but twice, where once you would change how far it goes, and the second sort of pass by would actually change even the closest encounter, right? So that you can start seeing how this is actually seems to be a really complicated scenario. Or it could have been exactly like you say, it could have been captured. It's another interesting scenario. And it's tough because that means you had to have a close encounter with another system, maybe, or this thing had to fly close enough to be captured. And that would have been tricky too, in part that, because I guess I should add this, if you want to be captured by the sun, it is not sufficient to just interact with the sun. Because if it's just two bodies, a planet and a sun interacting, by conservation of energy, if you weren't bound to begin with, you're not bound at the end of the encounter. So all that would happen is it would fly by, scatter off, and then fly away. what has to happen is that you fly by, also interact gravitationally strongly enough with the Jupiter, push the Jupiter a little bit aside to deposit some energy into the Jupiter sun system, and then due to that, you lose energy, and then you end up on a bound orbit, right? So you don't just fly by, you have to kind of push against all the other planets in the solar system, or some of them in the solar system.
Would you have to come fairly close to Jupiter for that energy exchange to?
I think so. I think this is actually a rather difficult simulation. Well, it's not impossible to do, but the number of options, the number of different ways of encountering the Sun-Earth system is actually, sorry, Sun-Jupiter system is actually, there's many different ways to do it, right? You can pass by fairly far, but then you kind of happen to scatter close to Jupiter, or you could also come from from the top view of the solar system, right? As in you come perpendicular to the plane of the solar system. So there's actually a very lovely thesis, master's thesis by a student who was essentially assigned by his advisor to explore all these options and just run the computer with thousands of simulations and see if any one of them work. And that was actually very helpful in our project later on. Talk about it if you want, but someone's done this study and it's not trivial.
Yeah, I'd like to come back to the dynamics of whatever the body is, black hole versus planet, and the rest of the solar system objects. But let's bring in first this alternative theory, which you and your collaborators have proposed, that it's not actually a planet 9, it's a black hole 1. I guess the first black hole in our solar system. What prompted that proposal? Was that to sort of resolve some of the concerns that we've been discussing about there being a planet out there, or was there another rationale to go in that direction?
Right. I think what really came about, the way this sort of came about was that James, my collaborator, went to a planetarium, saw a short movie about this possibility. And he thought, well, planets are great, but what else could it be? And so we started talking about this, and we realized there's a number of less, or let's say more exotic objects that would behave just the same way, and we wouldn't necessarily know better until we saw something. By that I really mean saw something in the telescope, right? Yep. And I don't think we were, we didn't set out to solve a problem like, oh, this is much more likely. We were sort of wondering, until you actually can visually confirm, or right, you should be considering all the options, as long as they're not absolutely impossible to happen. Right? And so we sort of thought about this, and several months into the project, we realized there was another observation by this experiment called Ogle, where what they saw was that there is a possibility that throughout the galaxy there are these black holes that are sort of small enough that they would have the same mass as this hypothesized planet 9. And so when you have sort of two anomalies with the same mass, you start wondering, okay, is this a coincidence, or if this is a sign of something, some kind of unified picture where this one object of the same mass as the other object I need for a different anomaly, maybe they're the same kind of object. And that's what made us think, oh, well, planet 9 could actually be, like you say, black hole 1, actually like that.
So you're throwing it out there as an option that is at least as viable as
or
9.
Let's say is viable. At least as
it's worth considering alongside rival possibilities. Gotcha. What is a primordial black hole? Because we need to be clear, we're not talking obviously about the kind of black hole I think most people have in mind, which is the sun or a star ends its life and it maybe explodes and what's left is a black hole. This would be much smaller, much less massive compared to conventional black holes. Where do these things come from?
So there's many competing theories on how you could possibly make them, but typically when you speak of primordial black holes, they're born when the universe is very, very early on during the history of the universe, when the universe is very dense, and there are what we call fluctuations in the density. In other words, some parts of the universe are slightly denser than others.
Right.
And this is purely statistical, as in this is not sort of necessarily given by any particular reason. Just there's some small fluctuations here and there. And occasionally you get a fluctuation that's bigger, by which I mean it's quite more overdense than the rest of the universe. And since the universe is already quite dense, it's possible that a small portion of this universe becomes so dense that it immediately forms a black hole, right? And so you can think about it as small pockets of the universe that just were dense enough to kind of go straight into a black hole configuration without ever having to go through a star sort of mid step, right? And because they don't have to go through a star mid step, they can be any mass, right? They're not bound below, right? The fact that they ever had to form a star. Right. So they could be literally the mass of a mountain, picture, I don't know, whatever, Mount Everest kind of collapsing into a black hole. They could be the mass of a large asteroid. They could be the size of the mass of the moon, Earth, up to stellar mass, and more than stellar mass. I mean, they could be hundreds of stellar masses, right? And these are all possible, and it very much depends on what was changing those fluctuations and allowing you to have maybe more fluctuations that you would typically expect. So there are theories that sort of suggest that for some reason there's some types of particles that actually drive the fluctuations up in a particular mass range.
Okay.
And that's how they could work.
So it sounds like there are different sort of theories, and so there may be more of like a range in terms of how many primordial black holes are likely to exist in any pocket of the universe today.
Exactly. You would expect.
What would that range look like, though? Can you can you estimate it? Figures?
It's a difficult one because I'm pretty sure that if I tell you that something is not quite possible, there's going to be a theorist that comes up with a good model that does it.
Of course.
But I should be clear. We have over the last at least 50 years, people have known. Actually, Hawking suggested this is possible. This is a Hawking idea, and ever since he suggested this, people of course went out there and said, "Well, can we actually look for them?" And for various signatures of these primordial black holes. And at this point, we have pretty successfully ruled out the scenario where the black holes are most of the dark matter, or are essentially the entirety of the dark matter, that, this missing component of the universe. So we know that at least they're less than 10% of the entire energy budget of the universe. They cannot be more than this small fraction, like 10% of the total energy budget of the universe. So we have experimental evidence that they can be too many of them. But we do not have I think theoretically, it's much easier to, of course, build theories that produce only very small amount of them, right? That's always easier. But people have successfully built theories that kind of go all the way up to the experimentally ruled out amounts of these. I don't know if that's a good answer to your question.
I guess you wouldn't see it exactly, but have we detected evidence of a primordial black hole?
So
they're small, I get it. It would be really hard to confirm that they're out there, but any kind of close to home that are candidates?
So we've never seen any one specific candidate that we would be sort of very much persuaded that they are. The way there's several ways to look for them, but the main way to look for them is you look at stars and you hope that maybe one of those primordial black holes passes in front of it, and that would actually change the image of the star. What it would do, in fact, counterintuitively, it would actually brighten it. And that sounds very strange, but what would happen is that the light rays that the star is emitting actually get bent, and some of the light rays that would miss the telescope, now they get bent into the telescope. And so actually more light.
Micro-lensing phenomenon?
Exactly, this is called micro-lensing. And so in fact, we would be receiving more light from that star for a brief amount of time when the black hole is passing in front of it. And that's how we look for them. And we have seen events that look like some stars got brighter than they went, for a brief amount of time. Okay. But many of those events actually correspond to just other stars passing in front of them, or brown dwarfs or white dwarfs, things that are fairly dim and you wouldn't see them alone. You just see the effect of their gravitational pull.
Got it.
And so far, people would say that we haven't seen them directly. Now, the Sobel experiment actually has seen 6 events that correspond to something passing in front of a star that we don't know what it is, and doesn't quite match onto the population of things we expect, except if there were quite few planets floating around, more than we expected, then that would be explained by just free-floating planets in the galaxy.
So again, hard to determine whether it's a planet or a primordial black hole
Exactly.
there,
Right.
just as it is in our
Yeah.
own solar system. But having said that, I just want to reiterate, I think, something you said, which is that according to theory, the primordial black hole size range would be kind of well within the range of what our planet 9 or primordial black hole in our solar system would, its mass profile.
Absolutely, exactly. It's forming something like 5 to 10 Earth mass of the primordial black hole is very much doable. What's kind of an interesting teaser for the particle theorists is that those primordial black holes that have the mass of a planet actually would be born roughly during the time when the universe had a temperature of order what we call electroweak scale, which is one of these particle scales that we very much care about, and it's connected, for example, to the Higgs boson mass.
Interesting.
I mean, at least it's in the same ballpark, but I think that would be a fair description. And so as a result, there's this tantalizing thing that if you actually see primordial black holes with that mass, there's a tantalizing option that that mass is really related somehow to Higgs physics, right? And that would be super exciting. I mean, you know, beyond the pale exciting, actually.
Yeah, that something so close to home could inform our understanding of kind of fundamental physics would be remarkable.
Exactly.
In terms of capturing a primordial black hole, you've mentioned some issues about how complex it would be to or improbable to capture a rogue planet and bring it into our solar system. And I guess the same is true of a primordial black hole, that the dynamics have the same kind of issues to surmount.
Exactly. You would have to actually just to make it clear how tricky, how kind of well aligned things have to be. The typical for a black hole, any object really that would like to be captured roughly by the Sun-Jupiter system, in order to have a reasonable probability of this happening, the velocity of this object with respect to the Sun would have to be only about 1/4 kilometer per second. And just to put this in the correct sort of terms, the Earth is going around the Sun with about 30 kilometers per second, right? So you can see how it would have to be somewhere around 120 times slower than the typical speed you have for a planet around the Sun, right? Because essentially, if you go any faster, it's very unlikely that you'll be able to encounter Jupiter just the right amount and then deposit some energy. Right? You also sort of whiz by so fast that it would be very difficult for you to lose any energy to get down. Right? So it has to be kind of a fairly well-tuned kind of accident, right, to be able to get captured. And this is true for a planet or a primordial black hole. And in fact, it sort of tells you that this is the perspective that tells you that those two scenarios are somewhat comparable, right? As in, at least both are fairly unlikely, but relative to each other, not so different. And that's what makes it a plausible scenario, right? In that sense.
Yeah, and in fact, I just wanted to quote from the article that your team put out. You wrote, "We will argue that while there is a low probability of capturing an Earth mass primordial black hole, it is no more improbable than capturing a free-floating planet of similar mass." But I think the other assumption within that statement is that there are at least as many primordial black holes as there are free-floating planets, so that the chance of capture, as unlikely as it is in both cases, is roughly comparable. Is that what theory tells us? That not just the mass profile of a primordial black hole, but also the number of these things is such that it could very well be that our so-called planet 9 is really one of these primordial black holes, that there's enough of them in the galaxy that there's at least some small chance we might capture one once in a while.
So actually, I think this is an excellent question, and it really goes to the core of the issue. And I'll tell you why. It's that we used the estimate for the number of typical sort of free-floating / rogue planets. And that estimate is that there's roughly about a couple free-floating planets per star, because you're assuming star forms number of planets and it loses some, and those are then the ones that we might capture, right? And then you compare it to what the Ogle experiment is telling us, that there's an anomaly and there's extra objects that they see lensing. And when you evaluate it in terms of how many black holes that would correspond to, per volume, right? You realize that the number of the black holes they see would be actually somewhere on the order of 300 times more than the number of planets you get.
Interesting.
So there would be many more of them, right? So it's actually, depends on how you, somewhere between, let's call it 100 to 300 times more, right? So there would be many more if this experiment, this anomaly proved to be correct. Now, on the other hand, planets tend to inherit the velocities of the stars they're born from, which are slightly slower than what the velocities of these primordial black holes would be, right? And so that means that more of those planets would be slow enough to get captured. And it actually turns out that those two effects, right? Planets are slower, easier to capture, but there's more primordial black holes on the other hand. Those two effects almost cancel each other out and get you sort of even 50-50 chance, right? And when we first got that result, when we sort of, put it down on paper, and we thought, this is a remarkable coincidence, right? I mean, it could have gone either way, but
sure.
Yeah. And so it's this kind of, it's a hilarious coincidence. And we didn't believe it. I think we redid the calculations several times because there was no good reason for it to be that way.
So you've put this out there for sort of scholarly consumption. That was last summer. And I guess obviously the follow-up question is, so what now? How are we going to determine whether this object is in fact a free-floating planet or a black hole? Are there any experiments being designed right now, or are maybe already available to us in terms of trying to settle this one?
Again, very good question. This is exactly the kind of thing you want to ask yourself. And I think there are ways to go about this. So this is what took us a significant fraction of the work, was in fact figuring out how would you distinguish and how would you find it if it was there. And then maybe I should just make it a bit clear that if it's a planet, the way you look for it is you look for the light that's reflected, the sunlight that's reflected from it, or from this infrared radiation, because this planet is slightly warmer than the surrounding space, so you expect to recover some infrared radiation from it. And there are in fact experiments that are looking for it, and experiments that are designed for other purposes that will be actually very useful in looking for a planet. And in fact, Brown and Batygin and Adams have really been looking for this kind of signature for a long time. And so essentially alone, if the anomalies persist and yet you don't find a planet, then you're kind of heading towards the right direction, right? Because you know that there's a gravitational object that doesn't do what a planet does. That alone, but I mean, it just makes the puzzle more and more acute, right? And the problem more and more acute, really. On top of that, sorry.
No, go ahead.
On top of that, how would you see if it is a black hole, right? And that is really the crux of the issue and the exciting bit. And we really tried to find a way. And unfortunately, black hole alone would be remarkably difficult to look for. And one of the things you would look for is this lensing event, right? But the problem is that although there are many stars in the sky, they're not there dense enough that you can hope that this object would eventually get to lens one, right? So you kind of, that's a slim chance. You would have to just get extremely lucky for that to happen. But we realized one thing, which is that primordial black holes, the way they are born in the early universe, if there is dark matter around, and we know that these primordial black holes couldn't be all of dark matter, so there still is need for dark matter in the world or in the universe. This black hole would actually slowly kind of assemble a dark matter halo around it. And some of the most common models of dark matter predict that this dark matter could be annihilating. In other words, dark matter particle means an anti-dark matter particle. They disappear, and out comes sometimes standard model particles like photons that actually, eventually you register as light, or X-rays or gamma rays or something like this. And because this dark matter has this, this black hole has this dark matter halo, it's And this halo is very dense, right? It's a very dense object. Annihilations are very common because it's very, since the density is high, a dark matter particle can very easily meet its antiparticle, right?
Right.
Since the density is high. And so as a result, these objects would actually glow very faintly in X-ray or gamma ray, right? And so as a result, even though we couldn't see the black hole alone, we could see the sort of effects of the dark matter halo around it. And so what we propose to do, and we're currently working on, is looking for all the possible records of the sky over the last, whatever amount of time we can get, actually. And look if we see a slowly moving source of photons on the sky, but not photons of the regular visible wavelength, but much, much higher energy, right?
Mm-hmm. And evidence of these annihilation events, in other words.
Exactly. And so one of the actually lovely things about this is that astronomers are very good at A, keeping their data very well recorded. B, the data sets are open. So as a result, you can go and actually there's this experiment that's been running for nearly 13 years, I think now, called Fermi-LAT, Fermi Large Area Telescope, that has recorded billions of photons and billions of X-ray, gamma ray photons. And you can go to NASA, download list of all of those photons, where they came from, at what time exactly they came, and then go to town and see if you can spot anything that's been slowly moving on the sky over the last 13 years, just in the same kind of orbit that you would expect Planet 9 to actually be. Right? And so we've been looking for it. It's not a trivial exercise. There's a lot of noise. There's a lot of background photons from other sources. On top of that, the telescope kind of doesn't have a full sky coverage. So what it does, it sort of wobbles on its orbit to kind of scan over the different parts of the sky. It sort of looks constantly in different ways. And so you have to be careful because this means your observations are time dependent. In other words, sometimes photons coming from a particular part of the sky are very likely to be detected, and sometimes much less likely to be detected. And you can see how time-dependent sensitivity can easily fake time-dependent signal, right? And so one has to be very careful about the analysis.
Gotcha.
So with that, and that's what we're doing. So far, we don't see one, but also we don't think we have the right technique yet. We haven't perfected the technique to be able to say there's nothing there, right? Maybe I should add, the one sad fact is that it also could be that even though there is a black hole, even though there is dark matter around it, simply the annihilations could be so infrequent that it wouldn't be enough to see it anyway, right?
But it is very much a thriving sort of research program, and so that gives you some hope that this may be resolvable. And I just think it's fascinating, the fact that this proposal you put out there is now finding connection to, as you mentioned, like fundamental Higgs boson physics, and now even, might help us understand dark matter better. It's just a great example of how science often moves us in unexpected places and finds weird kind of synergies between different domains of inquiry. So certainly will keep us going in terms of new areas of exploration on this fundamental question, I think, of what is our solar system composed of. And I would love to have you back on the show as new discoveries are made. But for now, I want to thank you so much, Professor Jakub Scholtz, for joining us here at the Star Spot. It's been a pleasure.
Thank you very much.